Hello everyone, and thank you for tuning into the Group Theory podcast. This is the show where we talk to working mathematicians about what it's like to do research for a living. My name is Logan, and today we're joined by Dr. Spiro Karigiannis, and I'm sorry if I pronounced that wrong.
Pretty good.
Oh, all right. He's a professor extraordinaire here at the University of Waterloo. Obtained his PhD in 2003 from Harvard University, where he wrote his thesis on deformations of G2 and spin 7 structures on manifolds. Now he's got 18 publications and over 250 citations since 2003. You may even know him as one of the top 14 posters on Math Overflow.
Really?
So, one of the top 14.
Yeah, I mean, that was true at some point. I haven't touched it in years, but that's amazing.
Oh, really? Yeah. Well, it's true. Without further ado, how are you doing today?
I'm doing well. Thanks for asking.
That's good. I'm glad to hear it. So I guess we'll just jump right in.
Mm-hmm.
What's your field of research, and how would you describe it to a non-math person?
Okay. So I study differential geometry and geometric analysis, and that's not the way I would describe it to a non-math person. I mean, what I would say is I study shapes in higher dimensions. And the usual question I get after that is, well, I know time is the fourth dimension, but what's the fifth or sixth or seventh? So then I can give you my stock answer when I hear that. If you want to hear it, I tell them, one can think of 3 dimensions of space and 1 dimension of time as a 4-dimensional space, but that's not the only thing, right? Anytime you have n number of parameters describing something, it's an n-dimensional space. So it doesn't have to have anything to do with physical space or time, although actually the things I study are of importance in physics. I study 7 and 8-dimensional geometric shapes called manifolds with special structures on them that are of use in theoretical physics, but I study them for their own independent interests. So it's great that we have physicists who are interested in what we do because they're sort of consumers of our product, but we would be producing it even if nobody was buying it because it's there and it's interesting.
Okay, yeah.
I could say more about it if you want to know more about.
For sure, yeah. If you could go into a little bit of detail. I mean, so your thesis here, G2 and spin 7 structures.
Yeah, I mean, I can say a bit more, but do you want me to keep it for a non-math audience or?
Like an undergraduate level, if possible.
Okay,
that's most of our audience.
Sure, undergraduate level is good. So a manifold, I mean, the sort of simplest way to describe what a manifold is something that if you zoomed in on it with a magnifying glass, it kind of just looks like a subset of Rn, an ordinary n-dimensional Euclidean space, right? So a one-dimensional manifold on a small scale, on a magnified scale, looks like the line, like R1. So it's a curve. It may be moving around. It may not just be flat or straight, but if you keep sort of zooming in, it looks flatter and flatter on a small enough scale. A 2-dimensional manifold looks like R2 locally. Locally just means sort of if you zoom in. So it's a surface, right? And you can have higher dimensional manifolds. If they're higher than 3, it's hard for us to draw pictures of them, although there are some tricks that we've developed to help have some kind of visual intuition. But mathematically, there's no difference between 1, 2, 3, 4, or 20 million dimensions. And the important thing about these manifolds, or one thing that's important, is that one way to sort of make precise the fact that it looks like n-dimensional Euclidean space on a small scale is that you can actually rigorously attach an n-dimensional real vector space to every point. And then, since you have a vector space, you can do linear algebra. So anything you can do in linear algebra, you can ask, can I do it to each of these vector spaces that are attached to every point on this manifold, and can I do it in some nice well-behaved way, some kind of continuously or smoothly varying way. And that's really what geometry is, what differential geometry is. And when you can do that, then you can ask, well, is there a best way? Is there somehow most natural way to do this? And usually that means you're looking for a solution to a natural differential equation. And then you're doing what's called geometric analysis. So it's kind of a marriage of algebra and analysis and topology when you're doing geometry. So my specific thing, there's this very strange algebraic structure in 8 dimensions called the octonions, which is, most of you know about the complex numbers. The complex numbers as a vector space is just R2, but there's a way of multiplying 2 elements of R2 to get another element of R2. This is complex number multiplication. And it's pretty good in that it's commutative and associative. Every non-zero complex number has a unique inverse. The only thing that you lose in going from the reals to the complex numbers is that it's no longer well ordered. There's no natural ordering on it, is a better thing to say. And then you can double that, and there's something called the quaternions, which is like R4. As a vector space, it's R4, and there's a multiplication on R4. The thing you lose there is they're no longer commutative. And then when you double again to 8 dimensions, you get what's called the octonions, and now these are no longer even associative, so they're really nasty things to play with.
Yeah.
Non-associative algebras are horrendous. And so a spin 7 manifold is basically an 8-dimensional space where each of these 8-dimensional vector spaces that we're attaching to each point has this octonion structure on it. And a G2 manifold is one where you have something coming from the 7-dimensional space. So I should have said all of these algebras have an identity, have an element 1, which when you multiply by 1, it doesn't change anything. And so that sort of picks out a distinguished 1-dimensional subspace, and then the orthogonal complement is what's called the imaginary elements of that space. So a G2 manifold is one whose tangent space looks like the imaginary octonions. That's sort of highly distilled. I'm sort of cutting out all the technical things, but that's basically it. And so I look at what kind of examples of such manifolds could exist. How would you construct them? If you have one, what nice properties does it have? For example, there's the way it's curved is special if it has one of these structures. You can look for special submanifolds, like subsets that have nice properties that are related to this special algebraic structure, and various things like that. So, I play with all sorts of different objects that are all related to these guys.
Okay. So this might be actually a stupid question, but so you were talking about how manifolds, if you zoom in far enough, it looks like Rn. Mm-hmm. Are there examples of, not manifolds, but like manifolds that are not, if you zoom in, that they don't have those properties? And are those a different area of study that are useful at all?
It depends. So you notice I didn't carefully define what it means to zoom in.
Yeah.
Right. There's various notions of what zooming in can mean, or what we say it looks like. So let me make it a little bit more precise. So a topological space is just something where you can have a notion of what it means for 2 points to be close in some sense. Mm-hmm. Where you can talk about convergence, and you don't even need a notion of distance. So for those of you who've taken any analysis, you know about convergence because you know about the distance between 2 points in Rn. But you can weaken that considerably. You can just talk about what it means for one point to be in a neighborhood of another point, and doesn't really need a notion of distance. So that's a topological space. And now if the space looks like Rn on a small scale, then you can use the usual distance in Rn in some sense to measure convergence and closeness. But then there's ways you can qualify what it means to look like. You can say that that if you take a small piece of your manifold, that it's what's called homeomorphic to an open subset of Rn. That means there's a continuous map which is invertible with a continuous inverse. If that's the case, that means that the notion of continuity is well defined. We know what the continuous functions are on this manifold, and we can talk about when two things are basically the same up to continuity. That's not enough to do calculus, though, because we can't take derivatives if we only have continuity. So if you want to be able to take derivatives, then you need to talk about what's called a smooth structure. And that means that we're saying that our manifold is not just continuously bijective to something in Rn, but the map is infinitely differentiable in some sense. Now, going through exactly the right definition would take too long, and it wouldn't be that interesting. But so there's one stage where you just talk about topology. That's talking about continuity. Then you add a smooth structure, then you can do calculus. You can do, derivatives and integration and things like that on manifolds. But then you still don't necessarily have a well-defined distance. You do in each small piece because you can identify, well, let me say it this way. There's no canonical way of measuring distance, because when I say it looks like an open set in Rn, there's no unique way that it looks that way. It's like in linear algebra, if you have an abstract vector space, you can say it's isomorphic to Rn once you pick a basis, but there's no preferred basis, there's no canonical basis. Same thing with the manifold. Locally, it might look like an open set in Rn, but there's no preferred or canonical way to make this identification. And so because of that, even though Rn has a notion of distance, because there's no natural way of choosing it to look like Rn, there's no preferred notion of distance. So you have to then add that as an additional piece of information. And that's when you do that, you're doing what's called Riemannian geometry. You're measuring distances and lengths and angles on your space, and that leads to the notion of curvature. So you can have two manifolds that are the same topologically, that they're homeomorphic, but they're not diffeomorphic. That means they have different notions of differentiation, of calculus on them. Or you can have two manifolds that are diffeomorphic. That means the calculus on them is the same, but they're not isometric. That means the notions of distances and lengths and angles are different on them. So your question was, can you have other things when you zoom in? Well, it depends what you want to study, right? If you want to allow yourself the ability to do analysis or talk about continuous functions or smooth functions, then you need some notion of closeness. You need at least a topology. There are other objects, certainly, that mathematicians study that are not as nicely behaved as manifolds, right? So you can have a topological space that's not locally Euclidean, it's not a manifold. And you can look at things like in algebraic geometry called varieties, and these are described as spaces of solutions to certain polynomial equations, and the polynomials don't even have to be over the real or complex numbers. You can look at them over some other field. And then the spaces you get tend not to be nice, smooth things like manifolds, but they're not so far off. So for example, if you're in R2 and you look at the x-axis and the y-axis together, the union of those two, then if you stay away from the origin, it's a manifold, because every point has a neighborhood which kind of looks like R, has a small neighborhood which looks like the real line. But the origin itself on that set, which is the union of the x and y axes, is not a manifold, because any neighborhood of it will have these two intersecting lines, and it has what's called a singularity, right?
Okay.
But you could still study it, you could still say things about it, you just need to sort of make your toolbox, depending on how you think about it, you either have less tools available because it's not a manifold, or you can say, well, I'm going to look at a more general class of objects, and so in some sense it's more liberating to do that.
Mm-hmm.
So that's one way you can weaken the definition, and there are many things that mathematicians study. I'm certainly not an expert in those, but another thing you can do is you can have it be infinite dimensional. You can have an infinite dimensional manifold, and then that kind of blows your mind when you try to think about what is it.
Yeah. Those visualization techniques will help with that one for sure.
It's after a while you have to try to let go of the fact that you can't always visualize it.
Mm-hmm. Now, another thing though that I think is particularly interesting, and I just actually finished a differential geometry course, an elementary introduction to it. And what I noticed was as we moved from surfaces to manifolds, you kind of add more restrictions as you generalize in a sense, but then that makes the math more powerful in a way. Like you can do more with it when you add more restrictions. Mm-hmm. And I don't know if that's like, can you speak to that at all?
When you add more structure,
yes,
then you are studying
it.
a richer class of objects, and so you expect to find more interesting information. So for example, right, if you just were studying, all possible two-dimensional manifolds, then let's say we don't have a notion of distance on them. They're just manifolds, and let's say we have a smooth structure so we can do calculus on them. Then in fact you can go a long way into saying what these are. These are in some sense completely classified. Let me make a couple of technical assumptions. If it's compact, that means it doesn't get too big, and if it's orientable, so it doesn't have crazy things like the Mobius strip or the Klein bottle, where you sort of walk all the way around and end up upside down. I mean, we understand those too, but it's just a more complicated answer. So let's say you're compact and orientable, then we know if it's a surface, if it's a two-dimensional manifold, we know that it's completely characterized by how many holes it has. It's called a genus.
Mm-hmm.
Right? A sphere has no holes, torus has one, and then you can have those inner tubes you go with the water slides for two people. That's a genus 2 surface, and you can have any genus you want. But that's a very sort of coarse classification, because all we're imposing is that it's a two-dimensional manifold with this compact and oriented assumption. But now if you wanted to put a metric on it, a metric is a way of measuring distances and angles, then you suddenly can have lots of different surfaces. So for example, the sphere, if I think of the sphere in R3, just the points that are distance 1 from the origin, that's a particular what's called Riemannian manifold, because I can measure the distance on the sphere using the notion of distance in R3, right? The closest distance between 2 points is what's called a great circle, or an arc of a great circle, which is the way planes fly over to go from point A to point B, unless you have to avoid some kind of restricted airspace. But then if you push that sphere down, make it kind of an ellipsoid, then as a smooth manifold, it's exactly the same one. It's what's called diffeomorphic. But as a Riemannian manifold, it's different, because now the distances on the sort of part where you push down have been shortened, and the parts that were pushed out have longer distances. So just on one smooth manifold where you consider all the diffeomorphic ones to be equivalent, you can have infinitely many distinct structures as a Riemannian manifold. Right? So we've put more structure on that space that we're studying, and now there's more possible distinct elements of that class.
So it's like it gives you a language to describe the things that are technically included in like the subset of all two-dimensional manifolds, but it gives you a language to kind of
It gives you a way to further distinguish them, to further refine them, right? So just to go back to linear algebra, right? We say every vector space, let's say n-dimensional real vector space, is isomorphic to Rn. That's true. If you want to not distinguish vector spaces that are isomorphic, then there's really just one given by the dimension. For each dimension, there's just one. If you are going to distinguish them by, if you are going to make a distinction between two vector spaces which are isomorphic but not equal, then there's infinitely many n-dimensional real vector spaces. But now let's say we identify them all if they're isomorphic. We just get Rn. Rn does happen to have a natural inner product, but we don't have to take that one. Or if our vector space wasn't Rn to begin with, and we're just identifying it with Rn by some chosen isomorphism, there's no reason why we should take the standard inner product on Rn. So just if you look at a fixed vector space, and now you want to look at it as an inner product space, there are infinitely many inner products on there. Right? But now you might say, well, I'm going to decide that they're the same if there's a linear isomorphism from one to the other that carries one inner product to the other. That's an isometry. Now you're saying, well, I don't care that there's so many different inner product spaces if they're isometric. If there's a isometry that takes one to the other, then I'm going to consider them to be the same. And then it's not hard to show that, again, any n-dimensional real vector space up to isometry is just Rn with the standard Euclidean metric. But this is not true on a manifold now, because even though on a manifold, if you have a Riemannian metric, if you have a way of measuring distances and angles, that means every tangent space has an inner product on it, right? And it's true that for each tangent space, you can always change your basis or have an isomorphism which will take you to the standard Rn with the standard Euclidean inner product. You may not be able to do that in a global, smoothly varying way. So two Riemannian manifolds do not have to be isometric just because they have the same dimension.
Okay.
But two vector spaces with the same dimension are going to be isometric. So the notion of now allowing your space to be not flat, not linear, allows a wider class of objects, right?
Okay.
So it's true that the sphere, I told you can sort of push it down and make an ellipsoid. That's a different Riemannian manifold. But there is a diffeomorphism that will take one to the other in this as Riemannian manifolds. It'll what do we say, pull back one metric to the other. And that's just this operation of pushing it down to go from a sphere to an ellipsoid is a continuous and reversible. It's even smooth and invertible with a smooth inverse operation. But so there was an example of two Riemannian manifolds that were not the same as Riemannian manifolds, but you can identify them if you wanted to by what's called a diffeomorphism. But if you have the sphere and the torus, you can't do that.
Mm-hmm.
And it's kind of intuitively obvious that you can't do it in a nice smooth way, because you would have to tear a hole into the sphere to do it. But you can quantify that in mathematics. You can assign. We do this a lot in geometry and topology. We assign algebraic data to a manifold or a topological space or a variety, and these somehow quantify or encode what properties these spaces could have. So the easiest example is what I told you about the genus of a compact orientable two-dimensional manifold. Is a number. It's a non-negative integer. And one of the first big theorems of geometric analysis from probably the late 1800s, I mean, really back then it wasn't called geometric analysis, but this could be seen as the starting point. One of the first theorems was the following. It says, if you have a compact orientable two-dimensional surface, then the question is, can you always find on it a Riemannian metric, a way of measuring angles and distances whose curvature is always constant? And now I'm not going to give you the definition of curvature, but intuitively we know curvature means how a space is curved. And the answer was, it depends entirely on this genus. So if it's a genus 0 surface, that's topologically a sphere. Maybe it could be deformed. It could be something where you sort of stretched it out, but you didn't make any holes in it. Then you can always put a metric on it which has constant positive curvature. Basically what that means is you can push it back into a smooth round sphere. And if you have something with one hole in it, no matter how horrible it might look, you can always sort of smoothly deform it to get a metric on it which has zero curvature. And now that's a little bit hard to imagine, because the usual donut we think of that we get at Tim Hortons and it's sitting on our table is not zero curvature. You can see it has curvature.
Mm-hmm.
But that torus is in R3. And there's no reason why manifolds have to be sitting in R3 or in any Rn. And if you take the two-dimensional torus as a space, there's actually a way to put it in R4 where the induced curvature is zero. It's a little hard to imagine if you've never seen it before, but it's pretty simple actually once you understand the idea. And then for a genus higher than 1, if it has more than one hole in it, there's always a metric on it which has constant negative curvature.
Mm-hmm.
So this is an example where knowing the topology of the space, right, knowing sort of very coarsely how it is up to allowing deformations and pushing and pulling and bending it, knowing that structure will tell you that what kind of geometry you can put on it, right? So I guess I've forgotten the original question you asked. I do this a lot, but what happens is in general in all the mathematics, right? You start with a certain class of objects and you can study them, and you can say, well, I want to study them up to this notion, this particular notion of equivalence. If they're matched in this way, I want to consider them as the same. And then you can study what kind of objects you can have. Then you can say, I want to put more structure on it. I want to have additional structure. Now it's a richer class of objects. And again, you can see two things that were the same before may now be different with this additional structure.
Okay.
Right? Then you can keep going and keep playing that game and adding more and more structure, and then you have more and more possibilities.
Of course.
Right?
Okay. Well, I guess we'll move on now, because we've been talking about that for a little while.
Sure.
When was it that you decided that math was the career path you wanted to follow?
I wouldn't say there was any single defining moment. It was sort of a gradual natural evolution. I always liked math as soon as I knew anything about it. Probably from kindergarten or first grade, I always loved math, and I never considered the possibility of not continuing to learn new math. Right. So it's going to be funny. It's going to date me though, because I'm in my mid-40s. When I was a kid, I was 3 or 4. I saw Star Wars, right? So I wanted to be an astronaut because I thought these are what astronauts do. They go around fighting aliens. I didn't know anything about it. So I wanted to learn more about what it means to be an astronaut. And then I started learning about planets and galaxies and whatever. And I thought, no, I want to be an astronomer. This is the cool thing. Right? I realized that the movie was fiction. So I wanted to be an astronomer. So I started to learn about astronomy. And then I got to physics. I thought, no, what I really want to do is do physics. And I started learning about physics. Then I realized there's a lot of mathematics. I had always been interested in mathematics, but then I got into the mathematics in physics. So when I was an undergraduate, I did both physics and math. And I wasn't sure what I was going to do after that. In fact, I hadn't even thought about graduate school. But at some point, in my third or fourth year, I was being told, well, you should think about graduate school and you should think about what you want to do. When I actually forced myself to make a decision, it was pretty obvious that I couldn't ever consider not continuing to do math. So I still like physics, and what I do is of interest to physicists, but I think I've forgotten a lot of the physics that I used to know. And my classmates who were in physics said I went to the dark side when I was doing but I could have said the same thing about them, I suppose.
Yeah.
So there was never any single moment.
Were there any particular math courses that stand out as things that kind of nudged you more towards math as opposed to physics?
That's a good question. I mean, it's more. I mean, I loved all the math courses. Is that true? I had to take probability and statistics. I was at McGill, where we don't have this artificial separation that we have here at Waterloo. So I took lots of differential equations, which I actually loved, but I also took probability and statistics, which I wasn't a big fan of. Every other math course I liked, but I would say more than that, the frustrating thing was in the physics courses where you needed all this math, and they wouldn't really tell you what it really meant because they couldn't, right? Mm-hmm. And it's not a knock on them because that wasn't what they did. A lot of the teachers I had in the physics courses were experimentalists. It wasn't their job to know why this math was true or what it really meant. They just needed to know how to use it to analyze their data. But I remember a few times where we were in a physics course and the professor was doing some kind of mathematics, and we kind of asked for the deeper meaning about it, and we couldn't get it. And I thought, well, I don't want to do this. I want to know what it is I'm using. So it wasn't so much that the math won over the physics, is that the physics lost.
Okay.
The math, is what I would say. And I did. I mean, I was an undergrad at McGill, and I did an NSERC USRA with Nikki Cameron, who used to be a Waterloo student in the early 80s. And that was my first taste of research. So that was really a turning point, I think.
Okay. But you also, you do, according to your website anyway, do some work with the Perimeter Institute for Theoretical Physics. Do you still, again, I imagine it's not physics related, but...
Well, I mean, as I said, the objects I study are of use in physics. I'm an affiliate member of the Perimeter Institute. I think most of the geometers in this department are. And that's because the main mathematical ingredient in modern theoretical physics is geometry and topology, and to some extent representation theory as well. They really use all of mathematics, right? But the sort of cutting edge new physics that they're still trying to understand is really heavy in the geometry and topology. So, if you've heard anything about string theory, they say the universe should be 10-dimensional, which is 4 dimensions of space and time, and then these 6 compact curled up dimensions. If you've heard people talk about M theory, that's an 11-dimensional theory of the universe, where you have 4 plus 7, and those extra 7 are these G2 manifolds that I study. Okay. Yeah, so the reason that happens, I can't really tell you exactly, but from what I understand in the physics, they want something called supersymmetry, which unfortunately the LHC is not seeing, so maybe it's not there, or maybe it's just there at higher energies. But they want something called supersymmetry, and if you translate that into a mathematical language, supersymmetry means that the manifold has what's called a parallel spinor. It's just some fancy way of saying there's some vector attached at every point to the manifold in some complicated way, which is somehow constant when you take its derivative. And we know exactly which manifolds can have one of these parallel spinners. In fact, the person who proved that is Mackenzie Wang and McMaster, just down the road, in the early 90s or late 80s. And so the list of which manifolds can have a parallel spinner, in other words, which ones can describe supersymmetric physics, is very small, and G2 manifolds are on that list. In fact, they're the only ones of odd dimension. Everything else is even dimensional.
Cool. That's a little above my head, but it sounds cool. And the one thing I got to give the physicists credit for, they're way better at naming things than mathematicians.
That's definitely true.
Yeah, they got way cooler names, but that's okay.
Yeah, we are. We have a lot of things in math called normal.
Yeah.
Or regular. This is really dull.
Yep, I agree. Now, so as a professor, you've got research responsibilities and you've got teaching responsibilities, and I'm wondering if you.
There's service as well.
Oh, really? So, well,
committees, serving on committees.
Okay, so out of all the responsibilities that you do have as a professor here, do you have a favorite between them?
Well, I mean, we all sort of see the service as some what's the word? Unnecessary is not the right word. It is necessary. Unpleasant, right? Something that has to be done but it's not what we want to do. Some of it is fun, right? Like if you're deciding on which students should win a scholarship or something, that could be fun. Or if you're deciding who to admit, or if we're revising courses, that could be interesting. Mm-hmm. But if it's sort of dull committee work that's just sort of paper pushing and going to meetings and voting on things, it's not pleasant. That's thankfully a small part of our job. It's like 20%, but it's not fun. For me, the teaching and the research go hand in hand. I mean, I know other people who prefer the teaching, and I know other people who prefer the research, but I would be unhappy if I had to do only one and not the other. In fact, sometimes when your research is stuck and you're not getting anywhere, you're happy to go into the classroom and talk about something you understand.
Yeah.
And to people who are hopefully interested in listening to you. And similarly with the teaching, right? After a long term of, talking about multivariable calculus for 12 weeks, it's good to have a bit of a break and say, let me go back to this research problem that had me stuck, before the course began, and see if I can look at it with a fresh set of eyes. I even think sometimes when I teach a graduate level course, or even an undergrad course if I've never taught it before, I usually get ideas for my research, right?
Really?
Because I think about, that doesn't mean, there's something in third year group theory that's going to help me prove a theorem. But it means that, you think about things in a way that you're not used to thinking about them. And if you bring that sort of mindset to your problem, you can have some insight.
I would also imagine that it's probably a good way to keep all of that stuff fresh. Because if you don't use,
Absolutely.
Algebra 1, you're going to forget it, right?
Absolutely.
I've already forgot. I would fail the exam if I had to take it today. So,
I probably would not do well in certain courses right now, the ones that I haven't taught in a long time. Yeah. It depends if you need to use the material on a regular basis or not. Right? So I use linear algebra all the time. And, analysis. Galois theory I've never used. I took it at one point. I loved it. It was interesting. I'm sure that I don't remember almost any of it. One day I wouldn't mind teaching it so I can refresh my memory, but it's not happening yet.
Okay. Well, speaking of, do you have a favorite course to teach or a least favorite course to teach?
That's dangerous to ask for least favorite.
You don't have to if you don't want to.
Well, I guess probably my favorite course is Pure Math 465, which is the Manifolds course.
Okay.
Just because I can actually get to defining what it is I study by the end of the course, at least a little to some extent. So that's a fun course. I've taught Math 247 too many times. It's fun, but I need to sort of rethink the way I present some of the material. When you've taught a course more than 4 or 5 times, then you start to hate the way you're doing it. And you want to sort of make changes. Yeah, every term I make a list of next time this is what I would do different, or that's what I would do different. But then you don't always have time to make these changes.
Okay.
And you forget, right? And then you're in the middle of teaching it again, halfway through the term, and you get to the the section on Lagrange multipliers, and you're like, oh, I remember, I wasn't going to do it this way again because something didn't quite work out well. In the sense that you make something unnecessarily complicated, right? And but then you don't have time to change it on the fly, so you end up re-delivering a lecture which you knew wasn't perfect to begin with. So yeah, there's some courses I've taught many times that once I sort of rejig them a bit, I think I'll be happy to teach them again, but not the same way again. I think the other courses I really like is the advanced linear algebra, 146, 245, because I use a lot of that in my work. And the knock that linear algebra has is like, oh, it's boring. It's not boring.
Those are really fun courses. I loved those ones.
Linear algebra is extremely interesting, and people don't give it enough credit. It's the number one most useful tool in mathematics. It's more useful in some sense than calculus.
Oh, I would agree, yeah, for sure.
I remember getting extremely annoyed when I looked in a textbook that we were using here for 136, the regular linear algebra, 136, 235. It was a decent book for linear algebra. I mean, they're all basically the same.
Yeah.
Unless they're advanced versions, there's not much difference. But this author had in the middle of his book, he had this essay like, why is linear algebra important? I'm going to convince the apathetic student who doesn't care for the subject and thinks it's dull and useless. I'm going to convince them why they should care. And that's an admirable thing to do. It's great that he tried to do that. And he started talking about all these problems that arise in science and engineering, physics, chemistry, biology that use linear algebra, which is good. And then he just shoots himself in the foot at the end of that essay saying, well, of course, most problems that arise in nature are not linear, so we can't use linear algebra. That's completely missing the point. I mean, I wonder what he was thinking, because the whole point of calculus is that if something is suitably regular, if it's differentiable, that means you can approximate it by linear maps.
Yeah.
And you can approximate a differentiable a smooth manifold by a vector space near a point. You can approximate a smooth map by a linear map. And so as long as you're staying in a small neighborhood of where you are, linear algebra is useful for any problem. And I don't think the students, maybe in our advanced sections they get that, but in the regular sections I don't think they're told that enough or often. They should be told that 5 times a term, and hopefully they'll retain it. But it's got this stigma that it's uninteresting and dull. I mean, now at least what we can tell them is, oh, when you search on Google, it finds what you want by computing eigenvalues and eigenvectors. I don't know how it does that, but that's what I've been told. And that's a cool thing to say to students.
Yeah.
But you don't need just that. I mean, linear algebra is absolutely everywhere.
I think probably the one reason is that it's more abstract than, say, calculus, and you learn even from high school the wonders of calculus. Look at how everything that calculus has brought us, and all this and that. And it's also easier to visualize. I mean, once you're in RN and you're looking at linear transformations, so I think the reason it's stigmatized is because we're sold this idea that calculus is the best thing that math has ever produced, which
it's not true.
Is definitely also debatable.
I agree, it's debatable, but I would also say that is part of it. I mean, the fact that linear algebra, I mean, the truth is, the mathematics of linear algebra is at least in the first year regular course, is much simpler than calculus. And so to make the course interesting and to make it have some content, we talk about abstraction and rigor and proofs, and some students don't like that. But so that is part of its sort of stigma. The other thing is it's taught by some teachers who don't like it and hate it, and it comes across. Part of the reason we have a problem with sort of math literacy in North America and Europe is because the people teaching it at the elementary school levels, they don't like it, right? And it's hard to hide it when you don't like something, and I don't think they even try to hide it sometimes. So if you have the body language, or even if you're explicitly saying, I don't like this material, the students are not going to like it. And a lot of the people teaching linear algebra don't like it for whatever reason. Maybe they never fully understood the reason it's so important. And it comes across. The message comes across.
For sure. Yeah.
It's too bad.
I agree, yeah. Okay, but moving on then, what was the first mathematical result you remember producing, even if it wasn't published, like you just said?
Definitely wasn't published. Well, it depends what you mean by result. If you mean where I actually proved something, that happened in my NCERC USRA. I think maybe the summer before that, I was studying these quaternions that I mentioned earlier, which is in 4 dimensions, and I was thinking, I knew the story that, so it was Sir William Hamilton, whatever his name is, Sir William Rowan Hamilton, the Irish guy, who discovered these, and he had been trying to find a multiplication on R3 that kind of behaved like the complex numbers, and we know now that you can't do it, it can't be done, and it's not hard to prove, and I knew that it couldn't be done, but I wanted to convince myself why it couldn't be done. Because I didn't know the proof of why it couldn't be done. And so I was playing with that one summer in McGill, in undergrad. So yeah, the summer of my second year of undergrad or something, I was playing with trying to convince myself why something couldn't be done in R3. Didn't really work. I couldn't prove it. But the following summer, I did an NCERC USRA 23 years ago, 1995, with Nikki Cameron at McGill. And I like to tell this story to my grad students who are frustrated with research and, think it's too hard. And anyway, let me tell you the story and you can decide whether I'm a sadist or whether I'm helping them. But so I had this undergraduate research project, and he described the question to me, and I didn't understand a word he said because I didn't have the background to understand the question. But he knew that, and he told me what to read, and I spent most of the summer, about 3 months, just digesting the material that I didn't know in order to understand what the question was. So it was something about differential geometry. I hadn't taken the course yet. It involved Lie groups. I didn't know what Lie groups were. It involved differential equations at a higher level than I was used to. So I spent the whole summer sort of teaching myself these things. And then finally I understood the question, and when I understood the question, he had also basically provided me with the tools to answer that question. And the question was, it's not going to make sense, but he wanted to show that the Willmore functional was the unique conformally invariant second order functional for surfaces in R3, whatever that means.
I understood a couple of those words.
I had to figure that out. And then I ended up proving it about a month after the summer was over, in my next term. And so I went to see him, and I said, "Oh, you're right. Your conjecture was right." He had completely forgotten. He said, "What conjecture?" I said, "That thing about the Willmore functional. I proved it, and it's true." And he said, "Oh, well, if it was that easy to do, then it must be well known." And then we did a literature search, and of course, not only is it in half a dozen papers from 20 years before, but there's one paper where they give a 3-line proof, and I had a 15-page proof. So that was a sort of a humbling experience, thinking that just because you got something doesn't mean nobody got it first. But it doesn't matter because I didn't see any of those things, right? I did get it first for myself. And so often, I'll have graduate students who come to me and say, "Oh, look, I got this," and I say, "Well, that must be," well, no, not because they're not smart enough to come up with something on their own, because I've been around a long time. I know sort of what areas have been studied well, what areas have not been studied well. And if they come up to me and show me something that was very easy to do, in the sense that, it may not have been easy for them, but when I see it, it's obvious that, yes, that should have worked, and someone should have tried that. So, I tell them it's probably known, and we look for it, and it usually is known, but that doesn't mean they should get discouraged, because they were able to find it without knowing that it was known.
Of course,
it's new to them. But of course, to get a PhD, you have to find something that's new to everyone, not just to
you. Yeah, of course. Well, I think the nice thing about math too is it's like everyone's on their own kind of personal journey, and so there's so many different ways to tackle every problem.
Absolutely.
And that's So I don't think it's too discouraging. I think if you have the gusto to prove something, even if it's already known, then that's great. Yep. So what would you say is your proudest mathematical achievement?
Ooh. Proudest. It's like having to choose your favorite of your children, right?
Yeah.
Luckily, I only have one child, so I can say she's my favorite.
There you go.
So there's, there's certainly one paper I have which is the deepest of my work, which is a new construction of these G2 manifolds that I talked about earlier, which involves a lot of difficult analysis and some difficult algebra and linear algebra as well. So that's sort of what's probably going to, at least in the first third of my career, stand out as the crowning achievement. But then there's another paper that, I don't know if proud is the right word. It sort of took more of my energy, more of my time. It's still a very, very good result. It's talking about these G2 manifolds when they're not smooth, when they have like sharp corners that look like cones, because somehow the physicists want these cone-like sharp points, and studying sort of if you had one of these, can you deform it in some nice way, or can you smooth out the sharp corner? So I did this work with somebody in London, and it's my second best paper, I think, but the process of writing it, submitting it, revising it from the referee's reports until final publication, for some reason took almost 5 years.
Wow.
which is a a significant chunk of my academic career so far, and so even though I think that's my second best paper, I put in more time on that than anything else. But then there's something else I'm working on now, which is not as deep mathematically, because there's not much analysis. It's more algebra, but I think it's really cool because I think I might have found a new class of objects that has evaded detection up to now. I haven't checked that completely yet. I mean, I found some new set of differential equations, second-order differential equations on manifolds, such that any solution to this sort of classical differential equation that's been known for 50 or 60 years automatically solves this other one. But I want to know, are there any solutions to this new one that are not already classical solutions?
Oh,
and I'm not sure yet. It's still open. It's still to be determined. But if there are some new ones, then even though there's no deep analysis there, that would be my favorite in terms of it was the most fun to do.
You think they'd name it after you?
No, they don't name things after people until they're, well, there's only two ways to get your name on something. One is to be long dead,
yeah,
right? And in that case, often they put your name on things that weren't really anything to do with you, right?
Yeah,
as long as you made a name for yourself. And the other way is to be, at a level where, I don't even want to say the next level. There's several levels above, right? Like these Fields medalists where they get things named after themselves.
Well, Dr. Ross Willard down the hall there, he's got Willard's finite basis theorem.
Oh, that's good.
As named after him, but it's been superseded apparently since he published it.
The other thing is I don't have the easiest last name to pronounce, and so often they'll avoid, if the name is hard to say, they just won't name it after you, right?
Yeah, I guess so. Yeah, that's the trouble.
Yeah.
Okay.
Change my name.
Yeah, maybe. Well, the flip side to the proudest mathematical achievement, what is the one problem you haven't been able to solve yet but would like to?
That's easy for me to decide, to know what it is, but it's not so hard to explain. So remember I was talking earlier about string theory, saying that it's 10-dimensional and it's 4 plus 6. These 6-dimensional things are what's called Calabi-Yau manifolds. So there's a whole bunch of ways to describe them, but it's not so important. But my supervisor was Yau, Xingtong Yau. He's at Harvard. Calabi he's still alive. I think he's 90 something. Calabi was a geometer who sort of showed that if you had a 6-dimensional manifold and you wanted it to be Calabi-Yau, which I didn't define and I'm not going to define, then something had to be true about its topology. There's no way that it could be Calabi-Yau unless what's called the first Chern class vanished. And what Yau did is he showed that thing that had to be true, that was necessary, is also sufficient. He showed that if the first turn class did vanish, then it was Calabi-Yau. Okay, we don't. What I would love to be able to do is have that was called the Calabi conjecture, right? And Yau proved it. So now these are called Calabi-Yau manifolds. What I would love to do is to have a version of that for G2 manifolds. We would like to say, if you had a 7-dimensional manifold, if it was a G2 manifold, then something would have to be true about its topology.
Mm-hmm.
And we would like to be able to say that if that thing is true, then it is a G2 manifold, that it's necessary and sufficient. But not only can we not prove that yet, we don't even know what that thing is yet. We don't know what the question is. But that's my sort of holy grail, right?
Okay.
That I've been trying to, on and off, think about that since grad school, whenever I have time. But I know that it's not, realistically, it's not in the immediate future, not just for me, but for the community. I think it's going to involve some advances that have not been made yet in terms of a new class of objects. I mean, we would get too complicated to talk about it here, but
For sure.
But I think it's not. The mathematical community is not ready for it yet. Maybe in 10 to 20 years it will be, but I don't think it's around the corner.
If you were able to solve it, let's say, is that like a problem that's like Fields medal worthy?
That's.
Well, I know it's probably tough to say whether or not something's Fields medal worthy, but is it in that same kind of class?
First of all, it's not. If you look at I don't want to knock all the Fields medalists have been fantastic mathematicians, but there's been some people who've been better mathematicians than some Fields medalists who didn't get one. There's a lot of famous, excellent mathematicians who never got a Fields medal for whatever reason, and then there's other people who they did good work, they did very good work, but then you compare it to some other Fields medalists and you think, oh, is this really on the same level as that? So there's, again, not knocking any of it because it's all fantastic work, but the level varies a lot.
For sure.
To answer that question would depend on how that problem ends up looking, right? Because if it turns out that it's unlikely. If it turns out that it's not that much different from what Yau did, probably not. It wouldn't be worth that because it would be just sort of a modification of something else that someone thought of first.
Okay.
If the problem turns out to be completely different, then it depends on what it ends up being, right? Depends on what tools are used. Usually the Fields medals lately have been given to people who sort of combine different areas of mathematics in a clever and unique way. I hate when people use the word unique that way, because as a mathematician, unique means the only thing. But in sort of modern society, the word unique means interesting, right? Or
I guess so, yeah.
No,
not before seen.
Yeah, exactly. So I don't think they give Fields medals to people who, unless they really do something spectacularly new, combining things that no one expected to be able to combine before. Now, I do know a lot of different areas of mathematics, but that it's hard to say what I'll use in my career and for what. So
yeah,
it's not really it's not something. Well, let me rephrase that. I'm too old for the Fields medal anyway.
Yeah, it's
I'm
like
going to be 44 on Sunday, so it's 40 is the age out, right?
Well, happy early birthday.
Yeah,
Yeah,
the Apple Prize goes to people who are in their 70s. So
yeah, so there's still that. Yeah, well, I've got 21 more years to win a Fields medal, so we'll see if I can do it. Probably not. Do you have a favorite theorem at all?
You mean the classical theorem?
Yeah, just doesn't have to be something that undergrads would know, but.
Do I have a favorite theorem? It depends, but again, what favorite means, right? So, I like when I'm trying to explain what proving a theorem might mean to someone who has no math background beyond high school. The thing I like to show them is why root 2 is irrational, because anyone can understand that.
Yeah, that's a classic.
So it's fun because you can show it to them in 10 minutes and they can understand it and they can be impressed. Then if you go sort of a little higher to the undergraduate level, I like this for example, showing that E is irrational is kind of cool.
Yeah, that was a nice proof.
But in terms of sort of my own research, what's the sort of I talked about the Holy Grail that I'm searching for. The one that preceded it, this Calabi-Yau theorem, is in some sense, it was the spark that ignited geometric analysis. I told you that it's been around for like over 100 years when this study of surfaces and what surfaces can have constant curvature metrics, but it didn't really take off until the mid to late 70s, right around the time when I was born, mid 70s. And it was when Yau proved this Calabi conjecture. That was really the first time someone used highly non-trivial, non-linear PDE methods, functional analysis, to attack a problem in geometry successfully. And since then, it's really taken off. I mean, it's there are numerous big theorems in geometric analysis, including the proof of the Poincare conjecture, which happened in the early 2000s.
Yeah.
Perelman's proof using Ricci flow. That's geometric analysis. So the things that have been proved with geometric analysis have been extremely surprising. So, for example, so my favorite would probably be this Calabi-Yau theorem, but a close second would be the work of Simon Donaldson in the early 80s, and that was his PhD thesis, and he was 21 or 22, and he got the Fields Medal for his PhD thesis in his early 20s.
That's gotta be, at that point it's all downhill from there. The first thing you do gets you the Fields Medal.
He keeps doing good work though.
Really? Okay. Wow.
So that, I mean, again, without going to the technical details, he studied if you have a four-dimensional manifold, then you can attach. I already said that you have this natural vector space attached at every point. But he said, suppose you put some other vector space at every point, and on these vector spaces you define some notion of calculus, of how to take derivatives. That gives you what's called a connection. And then he said, now let's look at the space of all connections on there that satisfies some nice differential equation that comes from physical interpretation, from minimizing energy of something. So now he's looking at the space of all what's called connections on a vector bundle over a four manifold. And this space is a very complicated space. But by studying the topology of that space, you learn something about the original four-dimensional manifold you started with. This is called an invariant theory of invariance. Now they're called Donaldson invariants. But it's a very, very complicated story. But the punchline that you can tell people that really shocks them, that they can understand. Remember I was saying earlier that you can have two manifolds which are homeomorphic but not diffeomorphic, or you can have two manifolds that are diffeomorphic but not isometric. So if you just look at Rn as a vector space, it's also a manifold. Of course, a little piece of Rn looks like Rn. There's nothing to do there. So you can say, how many different ways of doing calculus are there on Rn? How many different smooth structures are there? Can you have two copies of Rn that are not diffeomorphic? And it turns out, part of this was known in advance, and part of it was a consequence of what Donaldson did. If n is not 4, there's exactly one Rn. There's only one way to do calculus in Rn.
That's so weird. Why 4?
For R4, not only is there more than one way, not only is there infinitely many ways, there's uncountably many ways to do it.
What's so special about 4?
So the way you should think about it, I mean, one way to say it is, it comes from physics, so it's a magical number of space-time dimensions. That's not the right way to think about it. The way to think about it is as you increase the number of dimensions, things get more and more interesting because there's more room to move. But once you get too big, once you get bigger than 4, then you have so much room to move that you can show that two things that look different are really the same because you have a lot of room to maneuver and to change one to the other. So too small is too simple, too big is too big to be complicated. The magic number in the middle is 4, where things are just big enough to be complicated but not too big to be uncomplicated. It's bizarre, and if it doesn't blow your mind, then there's something wrong with your mind. But
that's fascinating.
So that's a cool result. I don't know how to prove that. I do know how to prove the Calabi-Yau theorem.
I'll have to look at. I won't understand a word of it, I'm sure, but I have to look into that because that's very interesting. Well, we're just about out of time actually, so I'll just got one more question for you.
Sure.
And that's what advice could you give to us aspiring mathematicians who want to one day be doing research?
That's the magic question. Well, there's lots of things I could say. The number one thing I would say is don't give up, right? It's hard. Not just, I mean, of course, if you want to be a mathematician, if you want to be an academic mathematician, the job market is pretty terrible because we produce many more PhDs than there are academic jobs for them. The good thing is if you have a PhD in pure math, you're not going to be unemployed, right? Because you're going to have anyone who has a PhD in pure math, is a smart person, knows how to think logically, and can find jobs. Unless you want to be unemployed, you will have a good job. If you want to be a mathematician, there's less opportunities. But if you really want to do it, you have to work really hard. You have to work really hard. What I was the graduate chair in this department for a couple of years recently, and what I would tell the students when they come in, I'd say, okay, here's our course, here's our degree requirements, right? You have to take X number of courses, you have to attend one seminar, you have to, pass some comprehensive exams or whatever. And then I would say to them, these are the absolute minimum requirements for getting this degree from this department. If you want to have a research career as a mathematician, you have to go way, 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 way above the absolute minimum requirements, right? Go to as many seminars as you can. Go to conferences. Read some papers. Read books that don't expect to only learn from courses. This is the other thing, is that almost all the mathematics I know I did not learn from courses, right? I took almost every course at McGill in math. But then I got to Harvard, and in the first year at Harvard, I learned as much math in that first year as I had in 4 years at McGill.
Really?
And after that, I keep learning. I keep learning more and more math every day. And most of what I know, I didn't learn from a course. You learn by talking to other people. You can read books, you can read papers, you can play with it on your own and try to figure it out on your own. So number one thing is you got to work hard, partly because of the environment, right? It was different. Even 50 years ago, it was different, right? There weren't that many people doing it, and if you were good at it, you could get a good job. Now it's not enough to be good at it, right? You have to work hard, and you have to be a little bit lucky. But you got to work hard. You gotta. I would say don't do it unless you love it, right? Because it's a difficult job, right? It sounds great. There's always these surveys that come out of the best jobs you can have, and mathematician is like in the top 10 always. It's a good job, but it's a lot of work, right?
For sure. It's
not a 40-hour-a-week job. It's not even a 60-hour-a-week job. So you could take a week off here and there whenever you want if you're not teaching, and nobody will say anything. But when we work, we work a lot.
And your brain never stops once you get that itch.
Yeah, I know that when I do a lot of research in the evening after dinner, I can't sleep after that because my brain is it's like it's on speed or something. So the advice is you got to work hard. Only do it if you really love it. I knew some people in graduate school who were really good at math. They were better at it than I was, but they didn't really like it. They were just there because they were good at it. And they got their degree, and then they didn't, or they quit, but then they moved on to something else. And I thought, well, why waste your time for 5 or 6 years doing this if you don't really love it?
Mm-hmm.
What else? What other advice could I give? You gotta definitely, you gotta be insatiably curious, right? You can't just say, well, I want to do analysis, so I'm going to take all the analysis courses, and I hate algebra or geometry, and I'm going to just avoid that. No, if you want to be a mathematician, you need to know a little bit of everything. You absolutely, more than a little bit, but you need to know a little bit of everything. If there's an area that you don't know anything about, you're not going to be able to make it. Because to see, especially now in this current environment, all the most important advances are made by combining different areas. And so if you've blocked out a certain area of math because you don't like it, then you're missing out. And you should ask yourself, why is there any area of math that I don't like? Right? Mm-hmm. There's some areas I like more than others.
Yeah.
But I'd still rather read a book on Galois theory than something on biochemistry or something. Not to knock biochemistry, but it's math is what I do for a living, and so I can't say there's anything that I don't want to know about math. Oh, here's one more piece of advice. Not so much an advice, it's an anecdote again of what I tell my graduate students. So I tell them that there are sort of, how many phases? There's 4 phases to the sort of evolution of a mathematician, right? Phase 1 is when you're an undergraduate student, and that's when you think you know everything. And of course, I'm generalizing, right?
Yeah.
But I mean, I knew a lot of undergrads, and I was probably one of them who thought they knew everything. Phase 2 is when you're in graduate school. That's when you realize, you don't know everything, but you think that one day you will. Right? Phase 3, when you're a postdoc, you realize, no, you don't know everything, and you never will know everything, and it kind of bothers you. Phase 4, when you become a professor, you're like, I don't know everything, I'll never know everything, and it doesn't bother me anymore, right? Because there's just too much out there. There's nobody. It's different from when it was, 200 years ago, where you can have mathematicians who knew everything. Mm-hmm. Now it's impossible. It's physically impossible to know everything, and you have to be able to accept that. Some people can't accept that, right? They're really bothered by that, and if you have that kind of personality, you're not going to succeed in this field.
Sure. Okay. Well, thank you very much for coming on the show. We appreciate it.